I'm going to do chapter 2.4 notes. So I've logged into Schoology. I now need to go to courses at the top, living environment period 4. I don't see what I need, so I'll go under materials all the way on the left. We are working on biochemistry, so unit 1, biochemistry. Chapter 2, the chemistry of life. I need 2.4. I have to scroll down until I find it, where it says chapter 2.4 video notes. And click on the little player button and play.
Here we are at our last section for chapter 2. This is section 4, chemical reactions and enzymes. Our key concepts that we're dealing with are what happens to chemical bonds during chemical reactions, how do energy changes affect whether a chemical reaction will occur, why are enzymes important to living things. And out of all of these, that last bullet is the one that is a theme that we'll carry out throughout the year.
Okay, so I'm actually going to pause it. I want to go back for a second. First slide. Let's see. Oh, too far. Key concepts. So she said the living environment, enzymes, important to living things. But this is going to be a focus for the entire year. So I want to make sure I pay extra close attention to this last bullet. It's obviously something important if she had to stop and make a comment.
Our key concepts that we're dealing with are what
So I'm going to fast forward a little bit.
to living things. And out of all of these, that last bullet is the one that is a theme that we'll carry out throughout the year. So when we talk about chemical reactions, we talk about the breaking and forming of bonds between atoms and molecules. Chemical reactions will change substances into different ones by breaking and forming different chemical bonds. The reactants are changed during a chemical reaction. So reactants are what we start out with. They're the ingredients for whatever it is that you're making. And the products are made, they're produced by the chemical reactant.
Okay, so reactants. This is good to remember. She gave me a good analogy. Reactants are like ingredients. So I'm going to make a little side note that reactants are the ingredients. If I can remember how to spell ingredients. There we go. Okay. And let's go back and hear that again.
So that's what you end up with. So if you're baking a cake, for example, your reactants are the ingredients like the eggs, flour, oil, milk, butter, whatever. And then the product is the finished cake. So think of a chemical reaction like that.
Oh, I like that.
Here we have reactants. The arrow, if you were to put a word in instead of the arrow means produces or synthesizes or makes.
Okay, so I really wasn't sure what this arrow meant, so I'm going to make a note because she told me what it meant. So I'm going to write that it produces or to make. I'm going to make a note of that because I honestly didn't remember what that meant. I really don't like cake either, so can I come up with a different analogy that's going to help me to remember reactants and products? The winter's coming, I love hot chocolate, so in this case, my reactant is going to be my cocoa mix and my hot water, and my arrow is going to produce hot chocolate. Just a different way to help me remember it. And I've got some vocabulary words here that I'm asked to highlight so I can make them stand out. My I should say reactants, caught my mistake. Reactants and my products. So I can go back and know that those are words that I need to know.
When you see it written, and we'll actually be looking at different chemical reactions during the year, and you'll have to understand that that's what the arrow means. Please make sure you are highlighting. So bond energy is the amount of energy that breaks a bond. And takes a certain amount of energy to pull these atoms and molecules apart. If you remember, we talked about covalent bonds and ionic bonds, and those are pretty strong bonds. We also have hydrogen bonds that are pretty strong.
Okay, so just as an example, the bonds that we've talked about, you know, just as a little reminder, examples, covalent bonds, ionic bonds, and hydrogen bonds are my examples of my bonds that I'm going to talk about this year.
Attraction, and these places where atoms and molecules are stuck together, it takes energy to pull them apart. And energy does get released when a bond forms between atoms or molecules. A reaction will be at equilibrium when the reactants and products are forming at the same rate. So here's an example. When we have carbon dioxide in our bodies, it actually has to form a compound with water, and that way it can be transported through your blood, and then you can exhale it at your lungs. And so what we see here is the reaction that occurs after your body produces carbon dioxide. It reacts with water in your body, and it forms carbonic acid so that it can travel in your blood, and then you can, at your lungs, it actually goes back to carbon dioxide and water, and you exhale that. And if you pay attention when you exhale, if you were to breathe on a mirror, for example, you actually form condensation, and that's the water.
Okay, so because I wasn't sure what some of these formula symbols were, I make sure that I write it down so that I know exactly what this combination is showing me. If I don't know what H2CO3 is, it's going to have a really hard time trying to figure out what exactly this formula and this reaction means.
Chemical reactions release or absorb energy. And activation energy is the amount of energy that needs to be absorbed to start a reaction. Any chemical reaction requires at least a little bit of energy input to get things going. And so you can think of activation energy like a hill. It takes certain reactions a lot of energy. Some reactions it doesn't require very much. But that hill, for example, is the activation energy.
Okay, so using my pictures here, I'm going to label this hill so that I understand a little bit clearly that the hill is the activation energy. I really wasn't sure what that picture was referring to. If it was the top of the hill, I wasn't really sure what that arrow meant.
You find the reactants before that hill, and the products are going to be after that hill.
Reactants.
And
so the reactants are at the bottom, and the products at the top. Again, I wasn't sure, so I'm going to label my diagrams so it gives me a little bit better understanding what it is that I'm looking at.
Exothermic reaction is going to release more energy than it absorbs. And if it were occurring inside of a flask, but like in the pictures that you see here, and you were to touch it, that flask would feel warm.
Okay, so that's kind of interesting information. So exothermic reactions release more energy, so it's a way for me to remember it. And because they release more energy, I could possibly feel heat.
An exothermic reaction releases more energy and it'll feel warm. The reactants will have higher bond energies than the products.
Higher bond energies.
Excess energy is released by the reaction. And here they're just showing you at the end, the products level of energy is going to be lower than the reactants.
Lower. So I can add that to my diagram.
Endothermic reactions absorb more energy than they release.
Ooh, that's good. Alright, endothermic. They're going to absorb more energy. So I got to think of a way to try and remember the difference between exothermic and endothermic reactions. Because exothermic actually releases more energy and endo absorbs it. What could I do? Let me think on that. So let's continue as we're doing that. I can see if I can come up with a way to remember the difference between endothermic and exothermic. Let's see.
The reactants will have lower bond energies than the products. And these reactions are going to feel cold if you were able to touch them.
Okay,
Energy
you're
is
going to
absorbed
feel
by the
cold. So this one's going to feel cold. Okay.
reaction to make up the difference. So here you see the product's energy level is going to be higher than the reactants.
So higher.
And honestly, the activation energies and endothermic, exothermic, those are all things that I'm explaining so that you can understand what a catalyst is and why that's important. So out of all of this, understanding what a catalyst is and an enzyme that we'll talk about shortly, that is the important part I want you to pull out of all of these.
Okay, so this is important. I need to know what a catalyst is. So I'm going to star this because this is super important. It's something I need to know. And let's keep going.
Chemical discussions. So a catalyst is going to lower the activation energy. It's going to make that hill smaller.
Okay.
The catalysts are substances.
Smaller hill. So when I look at my diagram, again, I can look and understand what it is that I am looking at. So a little side
Speed up
note.
chemical reactions. They decrease the activation energy, and they can increase the reaction rate. So here you can see the solid orange line is what the regular activation energy would be, and then the dotted line is what it is for a reaction that has a catalyst added to it. So it makes it easier for this reaction to occur.
Okay, I'm going to highlight that so I can pay attention.
Enzymes are types of catalysts. Enzymes are biological catalysts. Enzymes are catalysts that are going to be found inside our bodies, and they allow chemical reactions to occur under very controlled conditions. So enzymes, like I said, are catalysts in living things. They are needed for almost every single process that occurs in your body. If you did not have enzymes inside your body, you wouldn't be alive. Most enzymes are proteins, and this is something I don't believe I have you highlighting, but I think you should. This is going to come up multiple times during the year.
So I'm going to star it.
This particular.
Because it says I need to know this. It's not highlighted, but I'm going to highlight it, and I'm going to put a big star because it's something I need to know.
Or phrase that enzymes are proteins, and they're very specific. Their names usually end in ASE. If you recall before, I told you sugars end in OSE, but enzyme names.
Alright, so just as a little reminder, in case I forgot, sugars end in OSE. ASE and OSE. Just in case I can't remember.
Are going to end in ASE. And this will be important for you to know, because if you encounter a question that is talking about all these weird names, if you look at the ending and it ends in ASE, you know that they're talking about an enzyme. You don't have to know the name of the enzyme in most cases. You just have to know, oh, that's an enzyme, that means it's a protein, and then you can go on from there.
Okay, so I highlighted enzyme names usually end in ASE, and then sugars end in OSE, because it's obviously something I need to remember, and it's something that I can look for when I come across it in an activity or on a test.
Here's some example names: lactase, polymerase, ligase, and you're going to see these names again, but they all end with ASE, and they are types of enzymes, and usually they're named for what they do. Lactase actually breaks down the sugar lactose. Polymerase helps to build polymers.
Okay, so I'm going to write that down in case I didn't know. So lactase breaks down lactose. Oh, you know, I can't remember what she said about polymerase. Let me see if I can go back a couple of seconds. Just catch it again.
It breaks down the sugar lactose. Polymerase helps to build polymers.
Oh, builds polymers, okay.
Please make sure you highlight enzymes, very important term.
Ooh, again, noted.
Disruptions in homeostasis can prevent enzymes from functioning. Enzymes function best in a small range of conditions. Change in temperature and pH can break hydrogen bonds that are in these proteins, these enzymes. And an enzyme's function depends on its structure. This is a very key point that will come up again and again, is that an enzyme can only function if it has the right shape. Usually enzymes have only one specific thing that they can do, and they have to do it, or they can only do it if they are in the certain shape that they're supposed to be.
Okay, so I need to highlight this, that the enzyme's function depends on its structure, and that maybe most enzymes have one function. But I also think it's important that if it's telling me that changes in temperature and pH can break those hydrogen bonds, thus changing my structure, that's got to be important too. I really think that I need to write that down because those are two key factors that are going to affect the function of my enzyme. So I'm going to put stars next to these because these are two pieces of information I'm definitely going to need to know. And it was stressed in the video.
An enzyme structure allows only certain reactants to bind to the enzyme. These are called substrates. The specific thing that an enzyme works on is called a substrate. And they kind of fit together, enzymes with substrates, like a puzzle. And the place where the substrate fits into an enzyme is called the active site. And this diagram is showing you the big giant purple thing is the enzyme. It has a very specific shape. And then you can see the blue and the orange puzzle pieces. Those are the reactants for the substrate, and they fit in certain places on the enzyme. And that's the active site. The enzyme typically will not change shape during a reaction. It'll just help these substrates come together and change their bonds and form a reactant, or form a product. Please highlight substrates. So the lock and key model helps illustrate how enzymes function. If you think about how you have a lock on your door to your home and only a certain shape of a key will fit that lock, that's kind of how enzymes and substrates work. So substrates are brought together with an enzyme. The bonds in the substrates are weakened. They are changed, and the catalyzed reaction can then form a product, and then that product gets released from the enzyme.
Okay, so in this situation, so I'm thinking about it. So the substrate is kind of like the key because it's got a specialized shape. So I'm going to put my substrate as my key, and the enzyme kind of locks that key into place. So that's my enzyme is going to be my lock. Just to help me break it down a little bit and try and picture what it would be like if I was to actually use a real key and a lock, and what pieces represent which parts.
Enzymes in the human body will work the best at 98.6 degrees Fahrenheit or 37 degrees Celsius. When you get a fever, the doctors get worried when it gets too high, like 104, 105, because then your enzymes in your body stop working the way that they're supposed to. They start to fall apart. They lose their shapes. And that's a problem. You will die if your enzymes don't work. So if the temperature goes too high, the bonds in the enzyme will begin to break or denature. And if your body temperature goes too low, they don't necessarily denature, they just stop working.
Okay, so just as an example that I can write down to help me remember, that a high fever can equal enzyme denaturing, or enzyme breakdown, because denature is a tough word. So an enzyme breakdown, which can then possibly cause death. Just to give myself an example of how temperature affects me in the human body. And denature is our vocabulary word, so I'm going to make sure I highlight that. And it says it changes its shape, so I have to remember that denature means to change shape or to break down. Okay, start again.
Denature is a term that you're going to need to remember, so make sure you highlight that, please.
Highlight and star.
The ideal pH level, the acid-base level in your body for most of the enzymes is between 6.5 and 7.5, except in your stomach and your intestines, the pH is going to be much different, and those enzymes work better when the pH is very low. But if your pH goes too high or too low, the bonds in the enzymes will break or denature, and then the enzymes change shape. If they change shape,
You know what? I'm going to just highlight that break and denature again, because we're talking about pH and it's coming up with the same terminology. Break and denature. I just want to remember that because that's a key vocab word.
Do what they're supposed to do. The shape of the enzyme is very important because it has to fit exactly to the substrate like lock and key. Other things that can affect the rate of reaction.
I gotta go back. Just a few seconds.
Change shape. They don't do what they're supposed to do. The shape of the enzyme is very important because it has to fit exactly to the substrate like lock and key.
Wow, that's the second time, maybe even the third time that I've heard this. So I'm going to make sure I highlight this again because this was very important. It's obviously been something that's been talked about on more than one occasion, and I'm going to put a big star next to it.
Other things that can affect the rate of a reaction is the enzyme concentration. How much of that enzyme is available will determine how fast reactions can occur. So an increase in the amount of enzyme usually equals an increase of how fast the reaction happens. More enzymes means they are more frequently going to collide with the substrate. Also, substrate concentration, if there is more substrate to work with, more of the ingredients or reactants. An increase in the amount of substrate usually increases how fast the reaction happens. If there's more substrate.
So just as a little reminder that substrate, little arrow, is also a reactant. Okay, so I can make the connection.
Substrate, they are more frequently going to collide with the enzyme. So this last slide is probably the most important slide out of this entire slideshow, because for proteins it's the shape that matters. They do their job because of their shape. And remember, enzymes are proteins. If they have the wrong shape, they cannot do what they're supposed to do. So if you unfold a protein, it destroys its shape. If it doesn't have the right shape, it can't do its job. Unfolding proteins is called denaturing. And temperature changes can denature enzymes or proteins, and changing pH levels can denature proteins or unfold them.
Okay, so she said to know this. Make sure it's highlighted. Put a big no next to it, so I know exactly what I need to do.
That takes us to the end of our...
Where it says, and then begin test and quiz. So question 1, which of the following statements about enzymes is not true? Key word that I want to think about here is not true. So enzymes are organic catalysts, and I can go back into the notes and it says right here that enzymes allow chemical reactions. Enzymes are catalysts in living things. So I know that that is a true statement. Enzymes are proteins, and I highlighted that and have a star next to it. Enzymes are proteins, so that's true. All enzymes work inside cells. Not sure about that. And enzymes work best at a specific pH, and And that I know too because it tells me right down here the changes in pH have issues. And also, if I go through a little bit further, the ideal pH that most enzymes work between 2. So my correct answer, my one that's not true, would be C. Question 2, which of the following is a form of energy that may be released during a chemical reaction? Heat. I remember talking about heat because I wrote down a note to myself that I would feel something. Oh yes, endothermic I would feel cold, and in exothermic reaction I would feel heat. So that would work. Sound. I'm not sure about sound. Would there be a sound? That's a possibility. Not sure. Light. These things are going off. Bonds are breaking. Do I look at my charts here? Do I see anything about light? Again, not 100% sure. So, but then there is all of the above. Now, I'm not sure on this question. I'm going to come back to. I'm going to think on it. Let's go to question number 3. Identify the reactants in the chemical reaction. Well, if I go back in my notes, I made a note about this. So the reactants would be like my cocoa mix and hot water. So they come before my arrow. So I've got CO2 and H2O. Oh, look at this. I'm going to make a note on here too that these are my reactants and that this is my product. So CO2 and H2O, that would be my choice for question number 3. Those are my reactants. Question 4, what is the term used to describe the energy needed to get the reaction started? Again, I highlighted this in my notes. And it says the activation energy is the amount of energy to start a chemical reaction. So I don't even have to look at my other choices. I know that B would be my correct choice. And number 5, which of the following statements is true about catalysts? So I want to make sure I look in my notes about what catalysts are. And I even put a big star saying what I need to know. Catalysts lower the activation energy of a chemical. Oh, it does say that. Catalysts are used up during a reaction. All catalysts are enzymes. Catalysts slow down the rate of chemical reactions. Well, it says it increases the rate of reaction, so I know I can eliminate choice D. Decreases activation energy, okay? Lower activation energy. Catalysts are used up during a chemical. Well, it doesn't look like the catalyst is being used up, so I can't choose that one either. So all catalysts are enzymes. Enzymes are catalysts, as according to my notes. So my choice here, which one would be true, would be that catalysts lower activation energy of a chemical reaction. So let's go back up to question number 2. Which of the following is a form of energy that may be released during a chemical reaction? Well, the only one that we really talked about was heat. So I have to go with that because sound and light weren't chosen or weren't talked about. And